Yeah, our next speaker is Cristhian Garay, and he'll be telling us about evaluative aspects of differential algebraic geometry.
Thank you, Jack. Thank you to the organizers for having me here. Thank you all for being here also. It will be a pleasure for me to speak about some recent developments in the theory of differential algebraic geometry, understood as some zero sets of polynomials endowed with some action of differential operators in connection with combinatorics, namely tropical geometry. So I will be speaking about that. So my main goal is to study the structure of the set of specifically power series solutions to systems of algebraic differential equations. Don't worry, I will be introducing all these kind of terms and how the main tool is going to be related to some generalizations of valuations, which is a classical subject in algebra. But I prefer to refer to them as absolute values, which is more natural in geometry. So my plan splits into big chunks. The first one is some kind of preliminaries about these objects, and the second one to talk about applications of them. So here in the first part, I will be introducing the main players of this game, and everything. I will be speaking about commutative rings. So everything is going to be commutative and with unit. And I will also introduce some notions of absolute values. So also let me fix a field of characteristic zero for all that comes. And I will look at algebraic relations with coefficients in this ring of formal power series over with coefficients in K. And somehow I will be adding an infinite number of variables which encode the partial derivations. So I consider these kind of relations with these coefficients and making this statement equal to zero, making this object equal to zero is what I call the algebraic differential equation. So as I told you, I want to a geometric point of view in which I will be focusing in computing all the possible pairs of formal power series such that when I plug them into this statement, I get something which is true. Here I remark again that the sub-indices are meant to keep track of the order of the operator of the differential operators, and so this statement or this setting is valid for any number of variables in our ring and any number of power series in our solution set. I will be speaking here about 2 and 2 because I want to keep things simple. So the main question is a difficult one. I take any system of these guys and I want to know the nature of the possible pairs which solve this statement. So this is a big problem. It is not very easy to handle, but maybe we can say some things about it. Now, the second main point is that the notion of valuation, as I said before, it's very natural. So you just take a map which is multiplicative and satisfies this triangle inequality. And here I am using, note that I am using the multiplicative format for my abelian group, which has to be totally ordered if I want to discuss the classical situation. But these guys fit into a wider setting, which is that of idempotent semirings. Idempotent semirings are very natural objects from the point of view of algebra and combinatorics, since they are additively idempotent. That's to say that you don't get anything new if you sum A plus A. But the important thing is that they carry an order, which is you define A to be less or equal than B if whenever you make the sum you touch B. If somehow your order is total, that's to say any pair of elements are related to each other, then you fall into the classical setting of cruel valuations or valuations or absolute values of rank 1 or rank at most 1 or but if you allow yourself to work with this kind of objects, you get new things. Let me introduce an interesting example that I will be using here. To take the power set of n squared, this is just the positive part of the integers. You take that twice, and then you look at clouds of points. The union, you interpret it as a sum, so clearly the sum or the union of the set with itself is the same object, and the Minkowski sum as a product. So with respect to this structure, note that if I apply the definition of order, I get something which is not totally ordered. So this would be a semi-ring, which is not totally ordered. And if I look at the map, which to any power series associates the support, that's to say I just focus on the indices which carry a non-zero coefficient, then this is called a quasi-valuation. It's quasi because unfortunately or fortunately, this map is not multiplicative. So the first property of associated to the absolute value does not hold for this guy. Nevertheless, I can work a little bit more to turn this guy into a valuation. And what I have to do is just taking the relevant combinatorial information from these clouds of points. So what I do is I consider one of these clouds of points arising as the support of a power series. I take it and do a translation along all the integer points of the first quadrant of R2 with natural coordinates, and then I take the convex hull of that. As a result, I can compute some compact objects, which are the vertices that span this polyhedron. So sometimes if I do this process, I recover the same set. In that case, I call this a vertex set. And what I'm telling here is that the family of vertex sets, together with the usual operations of making the addition and product in the natural world of clouds of points, and then project again doing this combinatorial operation, it gives me a semi-ring. Of course, these semi-rings can be seen as a quotient of the previous semi-ring, which I said that it was not totally ordered. This guy is not totally ordered, but fortunately for us, the resulting map of sending a power series to the vertex set of its support satisfies the product rule. So in fact, this evaluation, or a generalized valuation, since the semi-ring is not totally ordered. And here I am showcasing some examples of the application of these operations to some particular cases of these triangles that you can see to the left. So this can be seen as a deformation of a very natural combinatorial structure that's called the semi-ring of lattice polytopes, in which the operations are usual convex hull of union and convex hull or Minkowski sum of polytopes. So the gray parts are meant to represent this deformation of the operations, and the white parts, together with the gray parts, are meant to represent what you would get if you just apply the traditional operations. Okay, so up to the second part, the most technical. To sum up, what I just did was to focus on the ring of power from a power series with two variables. Then I forget about the coefficients of this guy and just record the support or those places in which I have a non-zero coefficient. That gives me the support quasi-valuation, because this is not multiplicative, but if I project, if I take the vertex set associated to this cloud of points, then the composition is an absolute value. And I call this an generalized absolute value because this is not totally ordered. So just to keep track of my problem, my main focus is to say something meaningful about this possible, all the possible solutions, which are pairs of this power series that satisfy any system of differential polynomials. You may remember this from the first slide. So the first thing that I want to discuss here is that last year and this year we managed to show that this technology, this valuative technology, gives some meaningful answers, combinatorial answers. And I am grateful for the previous speakers that have already discussed some of tropical geometry. So if you go to the book of McLagan and Sternfels, there is a theorem which is called the fundamental theorem of tropical algebraic geometry, which is exactly this theorem that I am putting here. Just you have to take away the word differential, the word, and if you add the word differential to that result, then you get this one. So that theorem says that if you are interested in the initial parts of some solutions or to some algebraic variety over a valued field of rank 1, you have three ways to characterize that set. The first one is just solving it as an algebraic variety, and then taking the projection given by the valuation. The second one is to associate to any member of the ideal a tropical hypersurface, which is the support of a polyhedral rational complex, polyhedral complex, rational polyhedral complex. And then you make an infinite intersection or maybe a finite intersection, and you recover a subset also of R2 in this case, right? And the third one is that you have this valuation, which gives you a meaningful theory of initial ideals. So what I'm telling you here is that you can also use this diagram 2, which is the most important part of the theory, to introduce a theory of initial ideals, and you recover the same set as those weights, which such that when you do the initial degeneration of the differential ideal associated with your family is monomial. So this is exactly the differential version of that theorem. Of course, here we are interested in other objects, but this is like the result that I wanted to say today. But let me say something else. I have a commutative diagram here. You have classical objects. You have a ring or a domain. You have a fraction field of that. And you remember that you have here evaluation. So what I'm doing here is to extend this valuation, this absolute value that I have here in the left column to the fraction field. This extension is done the usual way. You take a ratio of elements of your domain, and since you have already there an absolute value, you extend it by applying it to each guy of your expression. So you define the unit ball. Since this is a metric, you can focus on the elements which have norm at most 1. So the classical theory tells you that if this valuation were cruel, R should be a valuation ring or a valuation domain. Since this guy is not cruel, you cannot expect R to be a valuation ring, but it is close to 1. Namely, this guy, which is the unit ball inside the fraction field, is a Bezout domain. And a Bezout domain is just a technical word to say that every finitely generated ideal is principal. And in the lower part, you can say you can see a semi-ring analog of the first row. So this is the value group of your ring. This is the value this is the value semi-ring of your valuation. This is the value field or semi-field of your valuation. And this is the value ring of your unit ball. So there are some remarkable things to say about this diagram in this slide. So it's worth saying that we discovered this organically. I mean, we were trying to understand what happened in this particular setting for differential equations, but later we discovered that this kind of theory had already been treated by people doing lattice ordered groups, which is also a remarkable branch of classical algebra. Its roots date back to Krull and Klein, I'm sorry, not Klein, Krull and other people doing studies about ideals. So yeah, you can say that a Bezout domain is the generalization of a Dedekind domain, since if you do the localization of a prime ideal, then this gives you valuation rings instead of discrete valuation rings. That's the first point. The second point is that the characterization of R as a Bezout domain gives you an easy way to compute or characterize flat modules. So this opens the door to do model theory, understood as flat schemes over some integral structure of your field. And what is more poignant or more remarkable is that there is a correspondence between the spectrum. So the spectrum of your ring, which is a classical object, is you can recover it as something which is called the K spectrum of this semi-ring. So recall that T plus is an idempotent semi-ring, so it is not a classical object with a combinatorial one. So the K stands for kernel. And we use this kind of things to somehow introduce order theory into the bowl. So you can recover some total orders in your lattice and square as maximal ideals of the spectrum of these guys. So yeah, orders play a prominent role here. And the last thing that I want to say is that what we are doing right now as a second application of valuation theory to these differential equations, algebraic differential equations, is that we want to use this technology of characterizing the maximal spectrum of this valuation ring or generalized valuation ring to try to push differential equations which have non-constant coefficients to ones which have constant coefficients, since we show that the quotient of the ring, of this ring, via maximal ideal, you recover your coefficient field. But this is a work in progress, and that's all I want to say. Thank you.
Thank you. Are there any questions for Cristhian?
Yes. Can I ask something, Jack?
Oh, please do.
Yeah. Hello, Cristhian.
Hi.
I have two questions, actually. Did you take
Please.
only two variables, P and U, just for simplicity? Or it's really important to have just two variables there? Another
Yes,
thing I want
thanks.
Okay, go ahead.
I'm sorry. Yes, here
No, go
for
ahead.
simplicity, I just yes.
Okay. And
It is possible to do this for more variables. You can put here as many as you want.
Mm-hmm.
And also you can put here as many as you want.
I see.
Yes.
Another question is about your generalized valuations. When you have classical crew valuations, you have important notions like, for example, the rank of the valuation, which is actually the rank of the totally abelian group there.
Yes.
And also, do you have such a thing for generalized valuations also?
We don't know.
Do they have a rank? Do they have a rank, for example?
Well, for example, if you focus on this first example, this tells you that this quasi-valuation lands on the power set of n squared, and the cardinality of this guy is the cardinality of the reals. So I'm not sure about these classical statements about embedding a group into a divisible group, which is just a bunch of copies of R with the lexicographical order.
Right.
But perhaps these are available for our friends in lattice order groups, which we are just starting to discover and to translate to this kind of language, because they tend to use some order language which is difficult to comprehend from our point of view.
I see.
So the answer is I don't know.
Okay. Thank you.
Thank you.
Are there other questions for Cristhian? Well, I had a bit of a vague question. So you have this machinery set up to study systems of algebraic differential equations and their solutions.
Yes.
I was wondering if there's something similar, a similar way to understand D modules in general.
That's something I really love to know. I'm just starting to shift to D modules because I don't understand well the technology.
Okay.
But perhaps via the theory of semi-rings, since semi-rings have a robust theory of modules, it should be possible to say something about this also. But we still need to learn the language and learn the technology to say something about it.
Okay, great. Yeah, thanks.
Thanks.
Yeah, are there any more questions? Okay, then perhaps let's thank Cristhian again.